Alright, in this video we study differentiation of univariate functions. Okay, let's start. First definition. Say we have a function f of x defined on some interval I, where this interval includes a point a. Okay, we say f of x is differentiable. Differentiable at x equal to a. When we say this, we mean the following. That is, this limit f of x minus f of a divided by x minus a and x approaches a exists. Okay, and when this limit exists, we write it as f prime of a, or df dx of a, or dx f of a. And these, so either this or this or this, whatever is fine. And we call them as a differential coefficient. Differential coefficient at x equal to a. Differential coefficient of f of x at x equal to a. Okay, this is defined at a given point x equal to a. But if differential coefficients exist everywhere in the domain of f of x, we simply say f of x is differentiable. So that is, if for every a in the interval, which is the domain of f, f prime of a exists, then we say f of x is differentiable. Okay, note that we don't say at x equal to a, but simply we say f of x is differentiable. That means it's differentiable everywhere in the domain. And as such, f prime of a can be considered as a function of a. So this one, we write it as f prime of x, so that this x looks like a variable. And that this function is called the derivative of f of x. Okay, let's consider a simple example. Suppose we have a function f of x that is equal to x squared. And this is defined on the entire real numbers. Okay, so let's find the differential coefficient at any point a, let's say. So f of x minus f of a divided by f of x is x squared minus a squared, x minus a. And if we factorize this, we have and x minus a. So x minus a cancels, and we have x plus a. And this converges to 2a as x goes to a, right? Therefore, the differential coefficient at x equal to a is 2a. And in fact, we can find this differential coefficient everywhere on the real domain. So we can say that the derivative of f of x is just 2x, as you know it already in high school. Actually, instead of using x and a here, we could have used x plus h and x. So instead of a, we use x. Instead of x, we use x plus h. And the difference between these two is just h, right? So we have x plus h squared minus x squared over h. And if you expand this, we have x squared plus 2xh plus h squared minus x squared here. But this will be cancelled. And we have h here cancelled, and 2x plus h, which converges to 2x as h goes to 0. So again, we have the derivative of f of x as 2x. So f prime of x is 2x, as we did before. Next, let's consider the derivative of sine x. So this is, by definition, is the limit sine x plus h minus sine x over h. So how do we find this limit? So to find this limit, if you look at sine of x plus h and sine of x, so we take this difference. Maybe you want to use some trigonometric formula, identities, right? So let's consider, let's recall the trigonometric identities. Sine of a plus b, let's say, is equal to sine A cosine B plus cosine A and sine B. And sine A minus B is sine A cosine B minus cosine A sine B. So if you add them, subtract them, then we have sine A plus B minus sine A minus B equals to, so this and this will be cancelled, and we have 2 cosine A sine B. So this is the difference between two sines, right? So it's kind of similar to this. So if A plus B is equal to x plus h, and A minus B is equal to x, then we can use this formula. Okay, so let's solve this. So if we add these two, we have 2a equals to 2x plus h. Therefore, a is equal to x plus h over 2. And if we subtract these two, we have 2b equals to h. So b is h over 2. So using this, let's see. So sine x plus h minus sine x should be equal to 2 cosine. So a is this, x plus h over 2, and sine b, so sine h over 2. So let's divide this by h, divide this by h. Then let's move h to 0. But we have here sine, okay. First of all, if h moves to 0, then this thing, cosine x plus h over 2, converges to 1, right? So cosine x plus h over 2 converges to cosine x, actually, as h moves to 0. And the remaining part, so 2 this thing times this thing divided by this thing. So 2 sine h over 2 divided by h. Now this is equal to sine h over 2 divided by h over 2. This converges to 1 as h goes to 0. Remember this formula? Therefore, so everything here converges to cosine x. So that means the derivative of the sine function is cosine x. And similarly, we have the derivative of cosine is negative sine x. So this is an exercise. You should prove this. Okay, next let's consider the derivative of exponential function. Okay, so this is by definition limit h going to 0, e to the power of x plus h minus e to the power of x divided by h. Now, let's find the limit of this. This is an exponential function, so we can factorize e to the power of x part. So e x plus h minus ex divided by h. So factorizing, we have e to the power of h minus 1 here and h here. So this is just a constant as far as h is concerned. Okay, now recall that this converges to 1. So as h goes to 0, the limit of this becomes e to the power of x. Therefore, the derivative of the exponential function is the exponential function itself. So it doesn't change by differentiation. Now let's think about the meaning of derivatives or differential coefficient. So suppose we have some function here and consider calculating the differential coefficient at x equal to a, for example. Okay, so we have a value of this, f of a here. Okay, let's say this is f of a, and let's take any x here. Okay, so that is f of x here. So the ratio f of x minus f of a divided by x minus a, this corresponds to this slope of this line, right? So this difference divided by this difference means the slope. Okay, now we move x towards a. So the slope will become like this, and at the limit of x approaching a, that slope corresponds to the slope of the tangent line at x equal to a. So the differential coefficient x going to a, f prime of a corresponds to the slope of the tangent at x equal to a. So slope of the tangent line. So since the slope of the tangent is f prime of a, and that tangent line passes through the point a and f of a, right? So this point here is a and f of a. So the equation of this tangent line becomes y minus f of a equals to f prime of a times x minus a. So this is the equation of the tangent line. And this tangent line gives some kind of approximation of the function itself. So let's consider this function again. So we calculated the equation of the tangent line. Yeah. Okay. So in general, this function is a nonlinear function. So it's a curved function. But around x equal to a, this is pretty close to this tangent line. So that means we can approximate this function by the tangent line. So this tangent line approximates the function. But the tangent line is, of course, it's a line, so it's a linear function. So the essence of the differentiation is a linear approximation of a function. Okay, next, let's show an important implication of a differentiable function. Okay, so here's a theorem. Suppose f of x is differentiable. Differentiable at x equal to a. Okay, then f of x is continuous at x equal to a. Remember, in defining differentiability, we did not assume continuity, right? So this is not actually trivial, but it's a theorem. Okay, so let's prove this. Now, since we are assuming that f of x is differentiable at x equal to a, from this assumption, we conclude that f prime of a, the limit, exists. Okay. Now, in order to show that f of x is continuous at x equal to a, we need to show this limit f of x going to a is equal to f of a, right? So this is our goal. So let's try to calculate this limit. Okay. And so how do we do that? f of x, we want to calculate this, okay? So f of x is equal to f of x, let's see, minus f of a plus f of a. Right? We just subtracted and added f of a. And now this part becomes f of x minus f of a divided by x minus a times x minus a. We just multiplied and divided by the same number, and f of a remains. Now, let's take the limit of x going to a. So this converges to f prime of a, and x minus a, x minus a converges to 0, and f of a is just f of a as x goes to a. This is equal to f of a. Therefore, the limit is equal to f of a, and we are done. You know, this theorem says if f of x is differentiable, then it is continuous. But the converse does not hold always. Okay, that means even if f of x is continuous, it doesn't mean that it is differentiable. So here is an example of a continuous function that is not differentiable. F of x equal to the absolute value of x. Okay, so if you plot this function, it looks like this. On the positive side, it's increasing, and on the negative side, it's decreasing. And it's continuous at x equal to 0. Right? So let's take the right limit. So to calculate the derivative of this, first consider the right limit, f of x and f of 0 divided by x minus 0, and x going to 0 from the right. Okay, so it's plus 0. So since x is positive, f of x is just x, and f of 0 is 0. So divided by 0, x and plus 0. So that is 1. So x divided by x is just 1. So this limit is 1. So the right limit is 1. Next, consider the left limit. Limit x going to 0 from the left. So f of x minus f of 0 and x. So since x is negative, the absolute value of x is negative x. Negative x minus 0 over x. And x going to 0 from the left. So this is negative 1. So the right limit and the left limit do not match. That means the limit, therefore, the limit of f of x minus f of 0 divided by x going to 0. Okay, so this is the limit, not right or left limit. It's just a limit. Does not exist. Therefore, it's not differentiable at x equal to 0. Okay, that's all for this video. See you later.